Welcome to this video on digital electronics. In this video, which is the first in the series of combination logic circuits, we will be looking into adders and subtractors. First, let us see what a combination logic circuit is. A combination circuit is one where the output depends only on the present input or the current inputs. As can be seen in the diagram, there are n inputs and m outputs. The outputs depend only on the present state of inputs. A combination circuit consists of logic gates that are connected in such a way that they produce a specified output for a given combination of inputs. Logic circuits are of two types: combination circuits and sequential circuits. Let us compare the two. In a combination circuit, as we have seen, the output depends only on the present input and no memory elements are present. Whereas a sequential circuit, the output depends on the current state of inputs and the previous output. So, memory elements are present. As can be seen in the diagram, the outputs depend on the input, the present input and the past outputs. We will be discussing about sequential circuit in later videos. First, let us look into a design of a combination circuit. The problem statement: design a combination circuit with 3 input variables that will produce a logic 1 output when more than 1 input variables are logic 1. That is, the output is 1 when more than 1 inputs are 1, and we have 3 inputs. Let us first draw the truth table. Consider A, B, C to be the 3 inputs and write down all the possible combinations of the 3 variables. So, starting from 0, 0, 0 to 1, 1, 1. Now, let y be the output, and the output is 1 when more than 1 inputs are 1, that is 2 or 3 of the inputs are 1, we have an output of 1. So, going ahead, 0, 0, 0 gives a 0, 0, 0, 1 is 0, and when it is inputs are 0, 1, 1, that is 2 inputs are 1, the output is 1. Similarly, for the rest of the content. Now, draw a K-map for this expression and we will get a simplified logical expression. So, we have seen how to solve a K-map and simplify a Boolean expression in the video on Boolean expression simplification. This is a 3 input problem. So, we have a 3 variable K-map and we have 2 power 3, that is 8 cells. So, fill the number of ones in the cell and simplify by grouping, and we get the logic expression as y is equal to bc plus ac plus ab. We have already seen how to draw a logic diagram from a given logic expression in the video on logic gates. Using 3 AND gates and an OR gate, the sum of product expression can be expressed as a logic diagram, and that gives the solution for the problem. Pause the video, solve this problem, implement a 3 input majority gate. A majority gate is one where the majority of the inputs are 1. So, since we have 3 inputs, a majority of input means 2 or 3 inputs should be 1, and it is the same as the problem that we have just solved. We will look into one of the important combination circuits, an adder. We will discuss about half adders first and then full adders. A half adder is one where 2 bits are added to give the sum and the carry. So, the block diagram of a half adder, 2 inputs, and we get the output as sum and carry. Draw the truth table for this. So, we have 2 inputs A and B. Write down all the possible combinations for A and B from 0, 0 to 1, 1, and the 2 outputs are carry and sum. So, find out the carry and sum. For input 0, 0, carry is 0, sum is 0. For input 0, 1, carry is 0, sum is 1, and for 1, 0 again it is 0 and 1. For 1, 1, the sum is 1, 0, that is sum is 0 and carry is 1. So, we have 2 outputs, carry and sum. So, draw K-maps individually for the carry and for the output sum. So, first the K-map for carry. So, since we have 2 inputs, it is a 4 cell K-map. Mark the ones where the carry is 1, and we see it is a single cell and carry is AB. Next, get the logic expression for sum. Draw the K-map for sum, mark the ones, and we see they are individual ones which cannot be grouped together, and therefore sum is A dash B plus AB dash, which is A XOR B. So, the logic diagram for a half adder is a XOR gate which gives A XOR B, that is a sum, and the carry is given by AB by an AND gate. Next, a full adder. A full adder is one which adds 2 bits along with its carry to give the sum and the carry output. So, 3 inputs to the full adder, A, B, C input, and the outputs are sum and carry. Now, going to the truth table for the same, the inputs, we have 3 inputs A, B and C input. Write down all the possible combinations from 0, 0, 0 to 1, 1, 1. Now, determine the sum and carry for each of these combinations. As we can see, for 0, 0, 1, add the first 2 bits A and B, then add it with C in, and we get sum of 1 and carry of 0. Proceeding similarly, adding 0, 1, 1, that is 0 plus 1 gives 1, 1 plus 1 gives 1, 0, that is sum is 0 and carry is 1. Similarly, proceed till the end. 1, 1, 1, 1 plus 1 is a 1, 0, plus a 1 is 1, 1, so sum is 1, carry is 1. Draw 2 K maps, one for the sum and one for carry, to get the Boolean expressions for the sum and carry. So, first the K map for sum, and we see each of the ones are individual ones, and so this is equivalent to sum is equal to A dash B dash C input, A dash B C in dash, and this term it is A B dash C in dash, and then it is A B C in, and simplifying them we get it as A XOR B XOR C input. Next, draw the K map for carry, group the ones, and we get the logic expression, simplified logic expression, and the logic diagram for the same is indicated. The sum can be obtained from a 3 input XOR gate which gives A XOR B XOR C input, and the carry can be implemented using AND and OR gates. Next, we will implement a full adder using 2 half adders. So, for this, use the expression of the sum, which is A XOR B XOR C in, and the expression of carry has to be rearranged a little so that it can be expressed as a result of 2 half adders. So, in this expression for carry that we have already got for a full adder, in the second term AND it with A plus A dash, and the third term is ANDed with A B plus B dash. Expand the series and combine, group them together again. So, this is equal to AB and this is A XOR B C. So, implementing using 2 half adders. Give A and B as the first input to the first half adder. The output is A XOR B and A B. Next, give this A XOR B and the carry as the input to the second half adder. The result is A XOR B XOR C, and that is a sum, and the carry that we get from the second half adder and the carry from the first half adder, OR them to get the total carry. So, this is implementation of a full adder using 2 half adders. Next is a half subtract. So, half subtractor subtracts 2 bits to give the difference and borrow as shown in the block diagram. Now, draw the truth table for this. The inputs are A and B, give all the combinations 0, 0 to 1, 1, and then give the outputs difference and borrow. So, 0 minus 0 gives a difference of 0 and borrow of 0. 0 minus 1, the difference is 1, borrow is also 1. 1 minus 0, difference is 1, borrow is 0. 1 minus 1, difference is 0 and borrow is 0. Now, draw the K map for that and get the expression for borrow, which is A dash B. Next, the difference, K map for the difference. So, mark the ones and we get the expression for difference as A XOR B. So, implement the expressions using logic gates. So, the difference is A XOR B and borrow is A dash B. Coming to a full subtractor, that is subtracting 2 bits with the borrow being considered, and the output is again a difference and the borrow. Draw the truth table, consider 3 inputs A, B and B input, write down all the combinations from 0, 0, 0 to 1, 1, 1. Now, determine the difference and borrow for each of these input combinations. So, 0, 0, 0 will give 0 and a 0 output, 0, 0, 1. So, first subtract A minus B, 0 minus 0, 0, minus 1 will give a difference of 1 and borrow of 1. Next is 0, 1, 0, 0 minus 1 will give a difference of 1 and a borrow of 1, minus a 0, it is the same. 0, 1, 1, 0 minus 1 gives a difference of 1 and a borrow of 1, and subtract 1 again from that, the difference becomes 0 and borrow 1. Proceed similarly, the last term 1, 1, 1, 1 minus 1 is a 0, 0 minus 1, difference is 1, borrow is 1. Now draw the K-map for each of the outputs, the difference and the borrow. So the K-map for difference results in an expression A XOR B XOR B in. K-map for borrow, mark the ones and group them, and the simplified expression is A dash B plus B B in plus A dash B in. Draw the logic diagram for the same, the difference using a 3-input XOR gate which gives A XOR B XOR B input, and borrow using AND gates, an inverter and OR gate. Let us implement a full subtractor using half subtractors, similar to how we did for a full adder using half adders. So use the expression for the difference, which is A XOR B XOR B in, and for the borrow, rearrange and get the expression which results in A dash B plus A XOR B the whole dash into B in. So the logic diagram using two half subtractors. The input to the first half subtractor is AB, so which gives the difference of A XOR B, and the borrow which is A dash B. Then to the second half subtractor, this A XOR B is given as one of the inputs, and the borrow in is given as the next input, and the total difference A XOR B XOR B in is obtained as the difference, and the borrow is the output of the second half subtractor and the first half subtractor are odd, and we get the borrowed term. In this video, we have first implemented a given problem statement using a combination circuit. Then we have seen the implementation of half adder and full adders, and half subtractor and full subtractors. These are the references.